This is video 2 of our chapter 16-17 acid-base review for the AP exam. Let's take a look at some free response questions. This is number 24. We have 3 beakers, each having 25 mils of a 0.1 molar solution. Here they are. Notice the concentration is the same. We have hydrochloric, ammonia, and ammonium chloride. Now realize that hydrochloric is a strong acid. Ammonia is the most famous weak base you always see. It's a good idea to remember ammonia as a weak base. And this is ammonium chloride, which is the conjugate base, conjugate acid rather, conjugate acid of ammonia. So this is ammonium. So these are actually connected. They're conjugates, is the idea. All right, and we're asked first to determine the pH of the solution in beaker 1. So because this is a strong acid, remember that strong acids dissociate completely, which means their pH is simply the negative log of their concentration. You don't have to do any icebox. You do iceboxes for weak acids and bases, but for strongs, you can go directly to the pH. So pH is simply negative log of the H plus concentration. In our case, H plus concentration is the same as HCl concentration because it's a strong acid. So we do negative log of 0.1. You can actually do this without a calculator, as I showed you in the multiple choice question. Since this is 10 to the negative first, logging negative 1 gives you 1. Get rid of that negative. Your answer is 1. pH does not have any units, so just leave it at 1. Make it look like 1 if you'd like. Right, so part B asks, all right, in beaker 2, we have ammonia reacting with water. It's a weak base, so notice it forms the conjugate, the ammonium, and hydroxide ion. The value of Kb is 1.8 e negative 5. We see that it's a weak base. Remember, weak acids and bases have small Kas or Kbs because of that reason. They want the Kb expression for the reaction. Now the expression is just a general expression saying Kb is products over reactants. So you should always be able to write the equilibrium expression. We've done this plenty of times. Now the thing to remember is that water is a liquid. Liquids do not go into the equilibrium expression. So really we have NH4. This, by the way, should be a plus. That was left off. Apologize. Times OH minus divided by the concentration of NH3. This would be the expression. Good? And now if we want to calculate the OH minus in the solution, we have to use an icebox. So we're going to actually use an icebox. Let me lower it a little bit here. And let's set up the icebox. And there was a shortcut to the icebox we taught you, but let me go through the icebox itself. Remember, the icebox, again, is used for weak acids and bases. So let me rewrite this equation out here so we can kind of see the process. So NH3 plus water, giving you NH4 plus and hydroxide. Right, our icebox tracks of what happens as we get to equilibrium. Remember, water, we don't really care about water as much. We begin, according to the 3 beakers above, at 0.100. These are zeros to begin with. So we have to subtract x here, add x. We end up with x, and 0.1 minus x for this concentration. And now we have to solve for the x, essentially. They want the hydroxide ion concentration, which notice is just the x here. So solving for x, we'll have to plug in the Kb, which is 1.8, 10 to the negative fifth, equaling x squared over 0.1 minus x. Now, if you were to try to solve this, this would require the quadratic. So remember what we did is we were able to get rid of the x because this number is 3 orders of magnitude different than this number. So this is e negative 1, e negative 4. We're actually at 4 orders of magnitude. So we're justified in removing x. And this is where the shortcut to the icebox comes. So then let's solve the equation as it is. If you move the 0.1 this way, you got yourself 1.8 e negative 6, because that times 0.1 gives you negative 6, equals x squared. So x is going to be the square root of 1.8 e negative 6, which gives us a value of 0.0013 molarity. So this is how you would solve it. Now the shortcut to the icebox, remember, and I would recommend doing the icebox so you can show your work on the AP exam, but the shortcut said this. It said that the OH minus in this case is the square root of your Kb times your concentration of NH3 in this case. It's essentially the initial concentration. If you had an acid, the shortcut would be H plus is equal to the square root of your Ka times your acid concentration. But that comes essentially from this equation, from the fact that we can get rid of X. Good? Right, so we have part C now. In beaker 3, we have a reaction that puts ammonium and go back to the ammonia. So beaker 3, remember, had ammonium chloride, which means it's a weak acid. This guy right here is a weak acid of the conjugate. It's the conjugate, essentially, of the base we just worked with. And so what they want is they want the Ka. Now there's an equation, Kw relates Ka times Kb. Turns out that Kw also gives you H plus times OH minus. And this is where 14 equals pH plus POH came from. So remember, anytime you have a base, you have to eventually subtract from 14. So this is the other definition that Kw gives you. Both of these equations are actually on the AP equations sheet that they'll give you. So we're going to use this one, which means our Ka is Kw over Kb, if we rearrange it, which means we got 1 e negative 14 or 1.8 e negative 5, which gives us a final answer of 5.6 e negative 10. Again, this is the Kb, I'm sorry, the Ka, the conjugate acid constant for NH4 plus. I'm doing this really quickly, so take a pause and think through it and look through it as you work these problems. Good, so we have double I, and it's saying that we're pouring contents of beaker 2 into beaker 3, and that we are mixing the solutions. So let's take a look at beaker 2 and beaker 3 again. So what you have in beaker 2, remember, is NH3. What you have in beaker 3 is NH4. So what you're forming is a buffer. You got yourself a buffer formed. Because remember, a buffer consists of a weak and its conjugate. So we have a buffer. Now, in order to calculate the pH of a buffer, and that's what they're asking us for, we'll have to use the buffer equation. There is a buffer equation on the, come down, here we are. The buffer equation is also on the equation sheet, and it says this: pH is pKa plus log of A minus over HA. Remember, this is pKa means negative log, which means this is negative log of your Ka, since this P is the operator negative log, that appears in pH, plus log, in our case, of base over acid. Remember that these are concentrations, but they can also be moles. So this would be concentrations or moles, and I would recommend oftentimes to use moles for this. It makes the problem much easier. In fact, in this problem where we have the two beakers, and each solution is actually at a 0.1 molarity, when you were to mix the two beakers, they'll actually dilute each other down. And so you'll have to make, sometimes you have to do dilution problems, which are kind of tedious. I would recommend just using moles. In fact, in this case, let's go ahead and use moles. Because we had 25 mils of each of these solutions, based on the diagram above, we can find out how many moles we have. So we have 0.025 liters times 0.1, which gives you 0025. So we actually have 0025 moles each of the conjugate and 0.0025 moles of the original base, which means our base over acid. Now your base is your NH3. So NH3 is your base, and NH4 plus is your acid. So this is acid. So what we have in the solution, let me get a little more room if I may. We have negative log of Ka. In our case, the Ka of our acid is the one we just calculated, was 5.6, 10 to the negative 10, plus log of 0.0025 over 0.0025. Now, you'll realize that these two numbers are the same, so this comes out to be 1. The log of 1, recall, is 0. But this whole part drops out, and it turns out that your pH is going to be the same as your negative log of your acid, which comes out to be pH to be 9.2 0.25. Now this is true, this is a good thing to remember. Anytime you have an equal amount of conjugate acid and base in a buffer, your pH that you're buffering is simply the negative log of your Ka. And this is actually a common idea. Apologize. So the next question is the resulting solution an effective buffer? Well, a buffer, remember, can neutralize either an acid or a base that was added. Wait a minute, we forgot to say that beaker 1, which has HCl, is now poured into this buffer solution. Now, because we have a buffer, the buffer will be able to neutralize beaker 1. However, in the beaker 1, we have the same concentrations. Beaker 1 actually had 0.1 molar, just like all the others, 25 mils of 0.1 molar. So you got yourself 0025 moles of strong acid in beaker 1, which means our buffer is able to neutralize it. Remember, this is our base of our buffer, is able to neutralize it, but notice how the amounts match up. If the amounts match up, that means both of them completely cancel each other out. So the buffer is over. Buffer is lost. And you would explain that because the same amount of acid was neutralized by all the buffer, all the base of the buffer, neutralized all the acid, the buffer is lost. And the best answer would be no, because it can no longer buffer. The buffer ability is lost. So now we have the last one to do, double I. And in double I, they want the final NH4 plus concentration in the resulting solution. And the resulting solution is from back here. So a quick little overview. We had a buffer formed. So we had the H plus, we had the NH3, and we had the NH4 plus. And so we added the strong acid to it, and all of NH3 now became NH4 plus. So we've essentially, the 0.025 now has added to the NH plus. So in the end, NH plus, NH4 plus, we have 0.0025 plus 0.0025, which was added from the base, giving us 0.005. So here's how many moles we have. I'll take a second to verify that, but the idea is we've neutralized all the weak base, and when a weak base gets neutralized, it becomes the conjugate acid. So all that we have of this now became this. So we have double of this than what we began with. They want the final concentration of NH4 plus. Well, concentration, you have to divide by liters. In our case, the liters was actually, we had 25 mils, and all three solutions were 25 mils, which means we have 0.075. And if we get the final answer, we should get ourselves 0.0667, 3 sig figs, because we have 25.0 and 0.100, it gives us 3 sig figs. This would be molar. And this is the final answer. So I went real quick, because I usually do in these videos, giving you an opportunity to stop and think through the questions, think through the concepts, and let's answer some questions about this in class.